Hi everyone, this presentation is for the instructional project of Geological Engineering course taught at Virginia Tech in fall 2009. We are Abira Batul and Uskritlayan, and the topic we worked on is rock failures in Hawaii caused by the October 15, 2006 earthquakes. We are going to give you an overview of our project in this presentation. Let's begin with the outline of what we are going to discuss in this presentation. First, we are going to briefly tell you about seismic history of Hawaii and characteristics of earthquakes that struck Hawaii in 2006. Next, there will be a discussion about performance and seismic analysis of rock slopes during these earthquakes. Then some failure mechanisms will be discussed that occurred during 2006 Hawaii earthquakes. These include failure of rock-cut slopes, stacked rock structures, and landslides. In the end, some concluding remarks will be made to wrap up the discussion. Let's begin with seismic history of Hawaii, and as seen from the figure, Hawaii has been target of many earthquakes in the past. Earthquakes as big as magnitude 7.9 have been observed. The reason of this high seismic activity can be attributed to volcanic foundations underlying the 8 islands of state of Hawaii. Actually, these islands are the result of single source of hot material rising from the mantle called a hotspot, as seen in the figure. So the crustal stresses imparted by this volcanic activity result in high rate of seismicity in Hawaii. 2 such seismic events were observed on October 15, 2006 in the island of Hawaii. First was Kiholo Bay earthquake, and it struck around 7 past 7 with a magnitude of 6.7. The focal depth of this earthquake was about 39 kilometers and it lasted for about 20 seconds. Second earthquake was Mahakona earthquake that struck around 7:14 am with magnitude 6, focal depth of about 19 kilometers and duration of about 15 seconds. Although these 2 earthquakes were less than 7 minutes apart, yet they were believed to be separate events due to difference in focal depths and epicenters. It is also believed that Mahakona earthquake may have caused even more damage than Kiholo Bay earthquake due to shallower focal depth.
Now let's see the actual footage of Kiholo Bay earthquake from Hana Hotel on Maui. Cameraman was shooting sunrise when the quake hit. Seismic rock slope stability is usually determined by pseudostatic stability analysis or Newmark analysis. In pseudostatic analysis, the limit equilibrium method of determining the factor of safety of a sliding block is modified to include the effect of earthquake on stability. In this method, ground motions are simulated as horizontal inertia force on the mass of the failure wedge acting in a direction out of the face. For Newmark analysis, failure doesn't necessarily occur when dynamic transient shear stress reaches the shear strength of the rock. If the factor of safety is less than unity at some time during shaking, it doesn't necessarily imply a serious problem. What really matters is the magnitude of permanent displacement caused at the times that the factor of safety is less than unity. The permanent displacement of rock as a result of earthquakes can be calculated using Newmark method. This is a more realistic and economical method of analyzing seismic effects on rock slopes than the pseudostatic analysis. There are mainly 5 slope parameters that have the greatest effect on stability during earthquakes. These are slope angle, weathering, induration, discontinuity characteristics, and water. Now on this decision tree, let's discuss how these parameters affect slope stability. As for slope angle, rock falls and slides rarely occur on slopes with angles less than about 25 degrees. For weathering, high weathered rock containing coarse stones in fine soil matrix and residual soil are more likely to fail than fresh rock. For induration, poorly indurated rock in which the particles are weakly bounded is more likely to fail than stronger, well-indurated rock. For discontinuity characteristics, rock containing closely spaced open discontinuities are more likely to fail than massive rock in which the discontinuities are closed and healed. And finally, for water, slopes in which the water table is high or where there has been recent rainfall are more susceptible to failure.
Now let's talk about some failure mechanisms. Many rock cut slopes failed as a result of 2006 earthquakes. It is found that there is a relationship between slope heights and the geology of the area. The two types of volcanic basalts found in island of Hawaii are AA, as seen in the left picture, and Pahoho, as seen on the right. AA basalts have rough surfaces and they are formed from the fast-flowing lava. These are generally found in the form of alternating layers of massive and strong basalt, which is surrounded by poorly bonded clinkers of various sizes and shapes. On the other hand, Pahoho basalt has smooth glassy surface with less clinkers and more massive rock, so they sustained better and showed less damage during the earthquake. It was observed that AA clinkers, which were already loose, got free from the overlaying massive rock blocks, creating the gaps. This resulted in the loss of strength for the massive rock blocks, as an outcome of which the slopes failed and rocks fell on the roads. This is seen in this picture. This also resulted in closure of roads for traffic, as seen in this picture. Highway 270 access road was blocked by the rock falls, as seen. Another failure mechanism that was observed during these earthquakes was landslides. Factors like frequent rainfalls, steep slopes, weak soils, and weathered rocks played a role in setting off these slides. This picture shows the falling of the cliffs near Kukya Bay during the earthquakes, with displaced trees at the base of the slope. Slide scars can also be seen in this picture. Another picture shows the cliff top that slid into the ocean, indicated by the displaced tree and the mostly submerged toe debris.
Now I want to discuss the failure modes of rock block structures when they are subjected to seismic loading. The first failure mode is the block-on-block sliding of columns, where stacked blocks of rocks move relative to each other and exhibit permanent relative seismic displacement. Second mode is the bending of a column or wall as a result of the structural response of the column or the structure that the column supports. Third mode is the sliding and dislodgement of blocks that could occur during earthquake loading of the structure that has been exposed to centuries of weathering and erosion. Fourth mode is the dislocation of walls due to differential settlement of foundation soils, which could take place under static or seismic conditions. Fifth mode is the wall-toe displacement due to core densification, where strength of loose soil, rubble cores, or backfill results in additional loading on walls. Sixth mode is the separation of block walls due to differing response of fill and exterior walls. Seventh mode is the loss of arch key block and deformation of arch legs. Eighth mode is the wall failure due to increased earth pressure of core or backfill, possibly by the elevation of water. Ninth mode is the wall deformation due to global instability, such as failure of the core or backfill, or a failure at the toe due to inadequate bearing capacity of the underlying soils. And the final mode is raveling, bulging, and slumping of the face of a rock block edifices, where, as wall slumps, blocks ravel, and as a result of progressive slumping, toe bulge, oversteps, and collapse occurs. As a result of 2006 Hawaii earthquakes, although many stacked structures were damaged, the observed effects weren't consistent. The most damage was suffered by tall and steep structures where contacts between rocks composing the structures were minimal. The church shown in this picture suffered almost complete collapse. The church was constructed of weakly cemented rock blocks in 1850s. An earthquake-related bending deformation occurred on a tall, freestanding, grouted, stacked rock wall at Spencer Beach Park. Other walls at the same park didn't show damage. However, none of the other walls were unrestrained like the one pictured here. These pictures show pre- and post-earthquake view of the entrance passageway into Puukohola Temple. The worst damage at the Puukohola Temple was to high retaining walls at the sole access passage. These two pictures are from another temple at Mailekine. After the earthquake, most of the interior face of the east wall slumped and raveled as seen in the picture.
In conclusion, Hawaii rests on seismically active region and will continue experiencing earthquakes in the future. It was observed that there was a relationship between geology and seismic performance of rocks, and presence of AA clinkers resulted in the failure of many rock cut slopes. Similarly, using unwanted blocks for construction of historic and cultural structures triggered many failures. On the other hand, structures with careful craftsmanship and finely fitted massive rock blocks survived better. Thus, many possible future hazards can be prevented by carefully considering the geology of the area and predicting the failure mechanisms from past experiences in potential earthquake events. In the end, we would like to thank Dr. Edmund Midley, as his work was a useful resource for us, and this ends the presentation. Thank you all for listening.